Hello, welcome to the course of feedback control systems. We start in this lecture with week one, of course. I will go through the slides that belong to this course, but I will skip the first slides where the way of working is explained, because that might differ a little bit from time to time. So I will do that in the lecture, the live lecture. And in this video lecture, I start at slide 7, which explains what the content is of the course for this week. I will talk about the basic terminology around feedback control systems, explain open loop, closed loop, static and dynamic behavior, the first introduction into the Laplace transform and corresponding transfer functions. And I will mention MATLAB. I will leave it up to you to learn MATLAB by yourself, but I will give a few quick demos about that. First of all, where are feedback control systems used? Well, actually, you could say almost everywhere in nowadays life. At home, you have a lot of systems that are controlled by a feedback system. In the workplace, in your car, everywhere you encounter that. It's really a very widely used technique. For example, your central heating at home, you have a thermostat at home, probably on the wall, and just by changing the temperature on the thermostat, you can make the real temperature in the room go up or down. So the temperature in the room will follow the set temperature on the thermostat. Similar for aircos, refrigerators and an induction plate where you cook your meal. An oven, it's all controlled by feedback control system. A feedback control system means you measure the current temperature, and if it is too low, you heat it up. If it is too high, you try to cool it down, or at least not heat it up further. And a lot of parts of cars, trains, traffic lights, and so on are controlled by feedback control systems. So just to emphasize the fact that what we are doing here is very common in your daily life, and especially in the field that you are going to work, embedded systems, controlling robotics, controlling motors, and so on. You will probably encounter feedback control systems. So here we will see how to use it, the basics. Keep in mind that it can be a lot of different things that are controlled here. It can be temperature or pressure or humidity, voltage, power, the speed of a car, and your cruise control in your car. It's also a type of feedback control system. It measures the current speed and compares that to the set speed, and accelerates if necessary or decelerates if necessary. So it can be about speed, it can be about the position of a motor, it can be about the temperature in the room, it can be the pressure in the system. Many different things can be controlled by a feedback control system. In this context, we will often talk about the process or the plant that is being controlled. So you have a process, and that process has a certain input and it has a certain output. And you want to control the output basically. So for example, an electromotor up here, it has an input, a certain voltage, you apply a certain voltage to it. The output is the rotation speed, more specifically, number of rotations per minute. If you increase the voltage, the motor will rotate faster, more rotations per minute. Or it could be a heater element, like here. Again, you input a voltage, the output is a certain temperature, and the higher the voltage, the higher the temperature. Or a more complicated device like a car. A car has a lot of possible inputs and outputs, but here in this example, we relate the speed of the car to the position of the gas pedal. So if you press the gas pedal further, the output, that's then the input, the output, the speed of the car in kilometers per hour will increase. If you release the pedal, the speed will go down. So all these things, we call them processes or plants. So that are two words that are used in this context. And they have a certain input, and depending on that input, the output will change. So yeah, in a more abstract theoretical way, we can show it like this. We have a process, can be a lot of different things. We apply a certain input signal to it, which means that's an input which varies by time. This could be the gas pedal in your car. Sometimes it's up, sometimes it's down. Depends on what you as a user, what you do with your foot. But it's a function of time, basically. The input is a function of time. Very often it's a constant line, so it's all the time the same. Maybe not in the beginning. So in the beginning it could be 0, and then at a certain moment you apply an input of 1 or 10 or 100, I don't know, and then that input stays the same. So it's often a very simple function of time, but it's always a function of time. And the output also. When the input changes, the output will probably also change. For input, we often use the word of the character X. For output, we often use the character Y. Those are basically functions of time. They change in time. If we have an open loop system, then what we do is just give the system certain input and then hope that it has the output that we expect and that we want. So like here we have a turntable driven by a DC motor. We have a battery and an amplifier, and we just give that motor a certain level of input, and then we are hoping, because we know the characteristics of the motor, and we know if we give it so much, so high in input, then the rotation speed will be that. And that you can sometimes read that simply in the specifications. So you apply a certain input and then you assume and you hope that the output, rotation speed in this case, will be what you expect. So that's the example of a turntable, more abstract. You have a desired speed, you have an amplifier that then calculates what the input should be. Then we have that input given to the motor, and the motor controls the turntable and gives it a certain speed. In a car, you keep your gas pedal at a certain position, and then if nothing else happens, then your car will have a more or less stable speed. But not always, as you know, you could have the wind against you or with you, so you go far slower or faster. You could go uphill or downhill, which will make the car go slower or faster. So it also depends on external factors, what the actual speed is. But in an ideal world, then a certain position of the gas pedal will relate to a certain speed, and the speed will stay the same if the input is the same. Similar with steering wheel. If you put your steering wheel exactly in the middle, you exactly in the center position, and you hope that your car will go straight. So if you are on a straight road, you will stay on the road. But as we all know, that is never the case. You always have to correct a little bit. So an open loop system where you give it a certain input and then hope and assume that it will have a certain output, that is only accurate in very special and restricted cases. So if the speed has to be a certain value, if you want to keep your car on the middle of the road, you have to make a closed loop system, which means measure the output and using that correct the input. Like here in our turntable example, we measure the rotation speed of the turntable with a tachometer and feed that back to the input. So then we have a closed loop system. And in that way, if you have a good, well-designed system, you can keep the output on not 100% exactly where you want, but very close to it. There will always be some deviations, a little bit too high, a little bit too low, but the system will correct that automatically. That's the idea. And yeah, it all has to do with this error. So what happens is that you have a desired speed as input. You have the actual measured speed as a feedback value. And these two are subtracted. So in the ideal situation where the measured speed is what it should be, equal to the desired speed, then your error would be 0. But in practice, it will always be at least a little bit off, so a little bit too high or a little bit too low. So then you have an error. If your speed is too high, since it is subtracted from the desired speed, there's a plus here and a minus here. So if your measured speed is too high, then the error will be a little bit negative. If you set it to 100 km per hour, but you measure 102 km per hour, then you have an error of -2, 100 minus 102. If your speed is a bit too low, you will have a positive error. And that error is used to control the motor, to make it go a little bit faster or a little bit slower. Yeah, I said kilometer per hour here. It is more like rotations per minute, of course, in this example of the turntable. For a car, it would be kilometer per hour. We call that desired speed the set point. And yeah, just keep in mind in the feedback control system, the error difference between the desired speed and the actual speed should be close to error. The system will try to keep it close to error, to 0, the error close to 0. Yeah, again, example of a car, because most of you know what a car is, of course, and how it is controlled. And in this case, the goal is to keep the car in the middle of the road. So we have yeah, these two lines, the line in the middle and the line on the side, and you want to keep your car in between those lines, which is actually a feedback control system, because you and your car together form that system. The set point, the desired goal is to keep the car in the middle of the road, more precise in the middle of the lane. The road has 2 lanes, of course. You are doing that. We are not assuming a self-driving car, so you as a driver, you are doing that. You are keeping the car in the middle of the lane. So your brain is actually the control logic. You control the car by using your hands. So as an actuator, to control the car, you have your hands. You keep your hands on the steering wheel, so that's the input of the car. Then the car is going in a certain direction. And what is the feedback? Well, that is simply your eyes. So you look outside, you see the road, you see the lane, you see the lines, and then you know if you are a little bit off to the left or to the right and how you should control it. So the eyes of the car here are actually the sensor that yeah, measure the actual position of the car and compare that to the desired position, which is in the middle of the lane. And then your brain automatically will correct that position. If you are a bit too far to the left, then you automatically steer to the right. If you are too far to the right, you'll steer to the left. That works automatically in your brain, but it is actually a feedback control system. Important observation is that the sensor here, your eyes, they could be disturbed, so they don't work 100% accurately. Like there could be distractions on the side of the road, like billboards, for example, or it could be raining, or there could be fog, or there could be something happening on the road itself. a car coming towards you that's behaving strangely, or I don't know. There could be all kinds of disturbances that yeah, interfere with this feedback loop. And yeah, keep in mind that there can be disturbances in the sensor itself. So your eyes could be not functioning 100% as they should, but it could also be that the car itself experiences disturbances, like when there is wind or a bad road, holes in the road, for example. And then it's a force on the car itself. And the other things I mentioned, like rain or fog, they don't really influence the car itself, but they influence your eyes and thereby the feedback control. So such a process like this, and that's an important observation, it's never ideal. There always will be disturbances from the outside, either directly on the process or in the sensor. A sensor is also, a real sensor is never 100% perfect. It also always have some kind of deviations. So the feedback control system that we want to use, yeah, it should be resistant to that. It should be such that it can cope with those disturbances. And in practice, they do. That's also why they are used so much. The standard, simple feedback control systems that we will discuss, they can handle these disturbances to a certain degree and still keep the car on the road. Okay, so that being said, about some examples, what you can think about. Then more theoretically, the type of systems, processes, plants, whatever you want to call it, that we will consider are only systems that are so-called linear and time invariant. So the systems that we consider, the whole theory behind feedback control systems basically assumes that our systems are linear and time invariant. What does linear mean? Well, exactly what the word says. The output reacts linearly on the input. So if you double the input, the output will double. If you have two different inputs and you add them, the outputs will also be added. Like, for example, here on the right, you have input 1 giving that output 1, input 2 giving output 2, and input 1 is simple, it's only a spike at time 0. Input 2 is also a spike, but then at time 4, I guess. If you add up these two inputs, then the outputs will also add up. We only can handle with our feedback control systems, we can only handle processes that behave like that are linear. And what does time invariant mean? Time invariant means that it should not matter when you give the output. If I give the same output now, or 4 seconds later, or a day later, or a week later, it shouldn't matter. Now, the systems that we consider, they should be time invariant. So that's the combination. It should be linear and it should be time invariant. Linear means, yeah, basically if you double the input, you double the output. And if two inputs are added, then the outputs are added. Exactly what you would expect from linear. And they must be time invariant, which is also very simple to understand. It simply means that in the system that we are controlling, it should not matter when we give a certain input. The output should always be the same, only shifted in time, of course. So if you have this input here at time 0, then you have this output. If you have the same input at time 4, you have the same output, same shape, but only shifted in time, a bit later in time. We call those LTI systems, linear time invariant systems. Most systems in practice are not exactly LTI. Your car is certainly not exactly linear, for example, but usually systems are LTI enough to be useful. So your car is not exactly linear. If you press the gas pedal twice as much as before, your car will not have exactly double the speed. So yeah, that's not the case. But around the set point, so if you want to control your car, let's say at 100 kilometers per second, then around that set point, let's say between 90 and 110, it is linear enough to be useful. So when I say we only consider linear time invariant systems, I mean that they should be reasonably linear and time invariant. I realize that sounds a bit fake, but it turns out that in practice this is very workable. And in practice, most systems that we want to control are LTI enough to be useful. But still, I want to mention it because for the theoretical understanding of our feedback control and the Laplace transform, it's important to realize that we actually want our system to be as LTI as possible. Then some input signals that we will often see. One of them is the impulse. That's the first one. Impulse input is an input that is almost always zero, except for one moment in time where it is very high. We also saw that here. Here's an input that's everywhere it's zero, and then at time zero, it has a peak. We call that an impulse input. And the unit impulse means that the integral of this signal is 1. Hopefully you know what an integral is, but I will not go further into that at this moment. So these impulse functions, we see them quite a lot. Another one that we often see is the step function. It's a bit different. That is 0 for a while in the beginning, and then suddenly at a certain moment in time, it makes one step to another value and then stays at that value forever. That's what we call a step function. And if the step has a height of 1, then we call it a unit step. So if we have here at time 0, if we have a step of 5, then we call it a step function, but not a unit step function. And if it has a step of 1, so it goes from 0 to 1, then we call it a unit step function. And also for the unit step function, this must happen at time 0. If it is not happening at time 0, it's not the unit step function. We also have unit ramp, which is 0 in the beginning, and then from a certain moment on starts increasing in a linear way. So this is a straight line, it's going up in a straight line. That's the ramp function. If it is a straight line with 45 degrees, so if you go up like 5 here, from left to right, you also go up 5 from top to bottom. So the x and the y, they increase in the same way. Then we call it the unit ramp. And otherwise we just call it the ramp. And one that also often occurs is the block wave. But you have seen that, I suppose, and that has a regular up and down rhythm. Could be used for plot width modulation, for example, or other purposes. What about the input? Impulse input means that the input is just one very short and hard kick. In the ideal case, it has a width of 0 and a height of infinite, and the integral 1, as I said. In practice, it's always a very short and high pulse, and the width is never 0 in practice. That's impossible. But we still call it an impulse if it's very narrow and high peak, and it's a unit impulse if the integral is 1. So the area below the graph, if it's 1, then we call it a unit impulse. Examples, practical examples: when you kick a ball, when playing football, the ball is lying on the floor. you give it a hard kick with your foot, well, then you are actually applying an impulse input to that ball. And as a reaction to that, ball will start moving. Or sounding a gong. So initially that gong is silent, no noise coming out of it. And then at a certain moment you give it a very short but very powerful kick with that stick. And then the gong will sound. So then you also give an impulse input to that gong. So we can do that in any system. So if you have a certain system here, you can always give it an impulse input. So sometimes it's shown with the character delta. It's the Greek delta. That means then an impulse input. So yeah, for any given system, you can always give it that input, an impulse input, and see what happens. Well, very often that system will then have maybe a behavior like that. So it will make maybe a few oscillations and then go back to zero. Or if it is the ball, it will move away and not go back to zero. It will not come back. That depends on the system. But you can always try it. With a given system, no matter what it is, a motor or a heater or a car, you can just give it an impulse input, a very short, very hard input, and then yeah, see how it reacts. Then the input is delta t, the output is a certain function, and it completely depends on that system, what function that is. We call that function the impulse response. So the response that the system gives when you give it a kick as an input, an impulse as an input, that's called the impulse response function. Very important. It really characterizes the system. If you know exactly what the impulse response is of a system, and if it is linear and time invariant, then you know the output for any input. So that's an important message. I hope you realize what I'm saying here. If you know the impulse response, if you know how a system reacts on an impulse input, then you can always calculate the output no matter what other input is given, if it is LTI. And that's what we are assuming. In real-life systems, the reaction to an impulse will always be after that impulse. It would be very weird if you kick a ball with your foot and the ball will start moving before you hit it. That would be very weird. That would be against all the laws of physics, against all the laws of logic also. So all the output, all the impulse response functions that we will see, they are all they start moving after the impulse input. So we assume the impulse is given at time 0. So the output will only start moving after time 0. And that's what we call causal. And again, realize it's very, very logical if you think about it, but it would be very strange if a system would start reacting before you give it an input. That simply does not happen in real life. So actually, I'm not sure if you realize that, but actually the examples that I gave here, they were not really causal. This was actually very strange. Here I said there is an input at time 0, a short pulse at time 0, and then this is the output. But in this case, the output was already changing, or it started changing around time -5. So it was already changing before there was any input. And yeah, that theoretically that's possible, but in practice that will not happen. So this is a system, a non-causal system. It is still LTI, it's linear time invariant, but it's not causal. So this will not happen in real life. A system will not react before you kick it. Yeah, and here you see reactions of different systems. So if you kick the ball, it will start moving. Yeah, it will not come back to you. The height, if you only look at the height of the ball, then you will see that after a kick, it will first move upward, and then at a certain moment start falling back to earth, and yeah, the height will go back to zero. But for example, the distance to the player, that will not go back to zero. The ball will not automatically come back to you. It will go away from you. So yeah, depends on which particular feature you are looking at, whether or not an output will go back to zero or not. If you look at the height of the ball, then it's going back to zero. If you look at the distance of the ball, then it will not go back to zero. That really depends on the system and what you are really looking at. Sounding a gong, so if you kick that gong, it will start oscillating. You will hear a very loud sound, and after time that will decrease and decrease and decrease, and in the end will be zero again. So this is a system that goes back to zero after an impulse input. But it has a very heavy reaction in the beginning, and goes yeah, smaller and smaller. Again, it completely depends on the system, what impulse response it has, and it also depends on what feature you are looking at exactly. Well, as I said before, but here it's repeated again because it's an important observation. If you have an LTI system and you know the impulse response function, then that system is completely defined. You know exactly how it will behave on any input. How can we calculate that? Well, what we can do is we can take the impulse response function, which is usually denoted by the character h, a small h. So the impulse response function, the reaction of the system on an impulse input, that's ht. If you take the convolution of that with the input, so if you give it not an impulse input but any other input, then you can take the convolution of the impulse response and that input, and that will give you the output. I'm not going to tell you what convolution is. You don't really have to worry about this to try to understand it. The important observation is, as I have said before, if you know the impulse response function, ht, and you know the given input, which can be anything, then there is a formula using this convolution. There is a formula that can calculate the output of this system. So that's what's meant with the sentence above here. An LTI system is completely defined by its impulse response function. If you know the impulse response function, you know how it will behave how it will react to any input. Yeah, most systems, they are after a while they stabilize. Either they go back to zero or they stabilize at a certain height. For example, this ball here. If we look at the distance to the player, then if the player kicks the ball will fly away. So the distance to the player will get bigger and bigger and bigger. But after a while, it will come to rest and stay on a certain position on the ground. So yeah, that's an example of what is meant here. If you have a system and you give it a certain input, it will change in the beginning, but usually, not always, but usually after a while, it will stabilize at a certain level. It can be zero, it can be that the system goes back to zero and that is the stable, the steady state, but it can also stabilize at another value. Also, this is specifically for a motor. A motor in the beginning, if you don't apply a voltage, it will not rotate at all. Then if you suddenly apply 5 volt, it will start rotating. It will not have its full speed immediately, but it will slowly increase. And then after a while, it will stabilize at a certain rotation per minute speed. So you have a transient interval where the output is changing, and you have a steady state area or interval where it does not change or not so much anymore. Okay, then we have to go to the S domain, which means we have to apply a Laplace transform, and that is the really powerful thing about this theory, that by applying a Laplace transform, we can make our calculations and our mathematics that we need much more manageable, much easier actually, because it is not that easy. This formula that I just showed, where the output is impulse response function convoluted with the input, that is a formula, and if you calculate that formula, then for any input you can always calculate the output, but this is not an easy calculation. A convolution is a difficult and time-consuming operation. So to avoid that, we go to the S domain. In other words, we apply a Laplace transform. And here again, I'm not going to explain what a Laplace transform is exactly. If you are interested, you will have to look that up yourself. And there are a lot of places on the internet that explain what a Laplace transform is. But as it turns out, at least in the beginning, in this course, where we only do the basics, you don't even have to know what a Laplace transform exactly is. The only thing you have to know is that if we apply a Laplace transform, then we go from the time domain to the S domain, which is more or less the frequency domain. And that makes our life easier in a number of ways. One thing that is becoming easier is that, for example, a derivative, if you take the derivative of a function in time, in the S domain, after applying a Laplace transform, it becomes simply a multiplication by S. And yeah, that is very much more simple than having to calculate or find a derivative. Finding an integral in the time domain, when we go to the Laplace domain, to the S domain, is just simply dividing by S. So these two, in itself, sometimes complicated operations, finding a derivative or calculating the integral, they become extremely simple in the S domain, just as multiplication by S or a division by S. That's one of the big advantages of going to the S domain, because we will have to do this a lot. Find a derivative or calculate an integral. As you will see later, we will have to do that a lot. And in the time domain, it's quite difficult. In the S domain, it's extremely simple. So that's one of the things that reasons that we like to go to the S domain. And the other one is that a convolution, we just saw convolution here, as I said, also a difficult operation. In the S domain, it turns simply into multiplication. So instead of finding the convolution of two functions, we now simply have to multiply two functions. And again, that is much simpler than a convolution. So that is the reason that we go to the S domain, that we apply a Laplace transform, because these things especially, they become a lot easier to handle. Yeah, okay, then what we now have to do is all our functions in time, we have to convert them into functions in S by applying the Laplace transform. So let's first look at the input signals. What happens to an impulse function if we apply a Laplace transform? Well, the Laplace transform will simply be 1. Constant value 1. That's simple. What will happen to the step function, the unit step function, if we apply a Laplace transform? It will become 1 over S. And unit ramp, If you look at that one also, if we apply a Laplace transform to that one, it will become 1 over s squared. So these three, it would be very helpful for yourself and save you time if you manage to memorize those. So the impulse function, unit impulse function, has Laplace transform 1, unit step function is 1 over s, unit ramp function is 1 over s squared. Especially the step function, that's one that you will use often. Okay, then what is the advantage of going to the S domain? Again, a derivative becomes multiplying by s, an integral becomes dividing by s, and a convolution becomes a multiplication. So why is that useful? If we do everything in the time domain, then if we know the impulse response function and we know the input, then we can calculate the output by doing a convolution. Difficult, as I said. But we can make it easier for ourselves by first applying a Laplace transform. So instead of that the input is a function x of t, it's now a function x of s. And for the S domain, we usually use capital, uppercase characters. For the time domain, we use lowercase characters. So this is a small x, and this is a big X. So what we do is we first convert both functions to the S domain by applying a Laplace transform. So then we get xs and hs, both capitals. And then calculating the output is very simple. That's now a multiplication. So we just have to multiply hs and xs, and then we know the output. That's an easy operation. That's one of the reasons that we use Laplace transform and that we go to the S domain. So it's easy to calculate ys, the output in the S domain. What we want to have, of course, is the output in the time domain. So there's one step left. That is an inverse Laplace transform. So ys, the output ys, has to be inverse Laplace transformed to get the output in the time domain. This can sometimes be difficult and sometimes be really easy, and we will stick to the easy cases, of course. And sometimes it's not even necessary. Yeah, it sounds maybe strange, but sometimes it's not that interesting what this yt is exactly. It's often enough to know the ys, the output in the S domain. And then an important thing to memorize again, this function that we saw here, the hs, which is the Laplace transform of the impulse response function. And remember, this impulse response function, let's go back, that is the reaction of the system to an impulse input. So if we give a short, hard kick to the system on time 0, then the output that we see then, that is the impulse response function. And the Laplace transform of this function, that is what we have here. And that is what we call a transfer function. And yeah, this is critical that you will not forget this word because we will use it so often. But this is a characterization of the system. So every system has a transfer function. Sometimes you don't know it exactly, so then you have to approximate it. Sometimes you do know it, but every system has a transfer function, which is the Laplace transform of the impulse response function. So the transfer function h is the Laplace transform of the impulse response function. Very often we don't even talk about impulse response function anymore. We only talk about transfer function. So very often, almost everything we do is only in the S domain, and we don't even consider the T domain anymore. But yeah, every system has a transfer function. Sometimes you know it, sometimes you don't know it, but every system has it. And yeah, if you know it, then it's very easy for any input x to calculate the output. because then the output is h times x. No matter what input you give it, x, you just multiply it with the transfer function, and then you get the output in the S domain. This y is h times x, where the dot really means multiplication. That is also a very essential one that you have to memorize. Or you can also do this, that's the same, h is y divided by x. Of course, you see that's the same as the y is h times x. So memorize at least one of these two, then you can always deduce the other one. Okay, here are some exercises which I will leave to you, and we can do them in the live lecture maybe. Here are some exercises. Let's have a quick look to see what is meant here. The first exercise is given a voltage divider. I hope you know that what it is. It's a network of two resistors. Calculate the transfer function for that voltage divider. So what it actually is, it's like this. So we have two resistors. The bottom one connected to ground, the top one connected to a certain input, and yeah, this is then considered the output. Well, to be consistent with earlier notations, let's call this one X and that one Y. Actually, the input, Y is the output. Each resistor has, of course, its own value. So this is R1 and this is R2. We don't know exactly the value, that's not given, but it has a value. We call it R1 or R2. And from this system, so this is the system, the process, we can quite easily calculate the transfer function. Given an input with the transfer function, remember, that is the output divided by the input. H is y divided by x. So for this system, how can we calculate the transfer function? It's a very simple system, and yeah, you know that the output y will follow directly the input x. I hope you know the formula for this system. Yeah, I'm not sure if I should give it now, but let's just do it. For a voltage divider like this, the value of the output is simply R2 over R1 plus R2. So a Y is this times X, or in other words, Y over X is R2 divided by R1 plus R2. But this is a well-known formula in electronics. I hope you are not surprised by this and you understand what I'm doing here. This is how a voltage divider works. So the output is R2 divided by R1 plus R2 times the input. And because of that, we automatically know what the transfer function is, because that's R2 divided by R1 plus R2. And yeah, let's assume that this is 100, this is 1000, for example. Just an example. That would mean that H is 1000 divided by 1100, or 10 divided by 11. Of course, H is always smaller than 1. Output is always smaller than input. It's not possible that it's bigger for an ordinary resistors. That is the intention of the first exercise. The second one, given a voltage amplifier with amplification times 100. Well, that's even easier. An amplifier is often shown like this, as you know. This one amplifies with a factor 100, so any input X is amplified 100 times, and then you have the output Y. So Y is 100 times X, or in other words, H is Y divided by X is 100. So the transfer function here is 100. So these are of course very simple examples, but in these simple examples, it's very easy to calculate the transfer function. This is especially easy because here always the output immediately follows the input. There's no delay. At least we don't take the delay into account. If there would be a delay, then things would become a bit more complicated. But here, if we assume that both this voltage divider and this amplifier, that they just change the output directly as a result of changing input, no delay or whatever, then it's very simple to calculate the transfer function. Finally, a quick look to MATLAB. MATLAB is a very much used elaborate tool for doing mathematical things. It's much bigger than what we need. We will only use a small component of it, which is this one here called Simulink. That's for simulating processes. It takes a while to open up. It's on my other screen. So if you open Simulink, you'll get this window, and then you can either open one of the earlier projects or start a new one. Blank model. Takes a while to open. But again, it's on the screen. Here we have it. This is a canvas on which we can start adding components, and the library of components is over here. What we always need is a source. That's something that generates a signal, and what we will use very often is this step function over here. That's a component that generates a step function. If we open it by double clicking, you see that it has an initial value 0, final value of 1. So it starts with 0 and makes a step to 1. So in that respect, it's a unit step. But you also see, and that's something to be aware of, that the step time is 1. So it does not make that step at time 0, but it makes that step on time 1. But you can change that if you want. So this is the input. What we also always need is a sink. That is something where the output is going to. And for that, we often use a scope, which just shows the signal, like a real scope would also do. And if we connect these two here directly, then I can open the scope, which is this. It really looks like a real scope. I can run this model. And then, you see the result. So I directly connected the input step function to the scope. So what we see on the scope is exactly what the step function does. It's 0 in the beginning, and at time 1, as you see, not at time 0, but at time 1, it makes a step from 0 to 1, and then it will stay at 1 from then on. This is not really useful. What we usually do at least is put a block in between. And for that, we have this transfer function block. Then the input goes to the system, and the output of the system goes to the scope. So this is our process that we want to control. By default, it has this transfer function 1 over s plus 1. Remember, we do everything in the S domain. We don't talk about T domain here in Simulink. We can change that. You can separately define the numerator and the denominator coefficients. So the 1 up here, that's because we have a 1 in the numerator. The denominator coefficients, it's 1 and 1. The first one is for S, the second one is the constant. So if I would, for example, use 3, 2 here, you see that the function changes to 1 over 3s plus 2. So it's always a polynomial in S. So if I would add another one, like 6, 3, 2, then we have 1 over 6s squared plus 3s plus 2. So both the numerator and the denominator are always polynomials in S. And what we define here in these settings are the coefficients of these denominators. If you want to have a constant, you can just use 1, for example, and maybe 5 here. So now we have a transfer function, like our amplifier, that has a value of 5. So it will multiply any input by 5, and that will be the output. So if we run this, you see it's still a step, but now it's multiplied by 5. So at time 1, that doesn't change, but at time 1, we make a step from 0 to 5 instead of 0 to 1 as we did before. So this is the simplest form of transfer function, just a constant that does not contain any s anymore. Of course, in the coming weeks, we will look at the more complicated transfer functions. If you want to make a feedback, let's also look at that. Then you have to add this component here that sums up two inputs. Well, we don't actually need that. What we need is a subtractor. So that does a plus and a minus. So I replace the second plus by a minus. If you look closely now, you see it says plus on the left and minus on the bottom. That it could be connected to the system. And then here we would have the feedback value. So yeah, in this way, this is too simple to be useful, but in this more or less in this way, you can make a feedback system. Well, that's of course what we will look at in the coming weeks. So what feedback system has is this plus minus, this subtractor, and a feedback value. So that concludes our overview of the second order systems. In the remaining slides, we look at something else, so-called reduction rules. That's about how, if we combine a number of processes, how the transfer functions of these processes can be combined. And we have three rules here: the product summation and the loop reduction rule. The first two are actually very simple. The product rule, for example, that's if we have two processes in sequential order, so we have an input X that is going to a process H1, this transfer function H1, and the output of H1 is the input for H2, and then the output of H2, that's the output of our whole system. So here we have a combination of two sequential processes. And each processor has its own transfer function, so H1 for the first, H2 for the second. Then the transfer function of that whole system, that combination of two sequential processes, that will, can be easily calculated. That's H1 times H2. If you look at the output at this stage, so what's coming out of the first process, that's H1 times the input, H1 times X, that's the input for H2. So what's coming out of H2, that's H2 times the input of H2, which is H1 times X. So the output of H2 is H2 times the input of H2, which is H1 times X. So yeah, and it's a multiplication, and the dot here is simple multiplication, so you can change the order, H2 times H1 or H1 times H2, that doesn't matter. The transfer function of this whole system, this combination of these two systems, it's simply H1 times H2 or H2 times H1, whatever you prefer. It's the same. So that's what we call the product rule. Very simple. If you have two processes in succession or sequential, then the transfer function of that whole is the multiplication of the two separate transfer functions. Similarly, we have a summation rule, which is about two parallel processes. So suppose we have two processes, H1 and H2, which are not sequential but in parallel, and the outputs of the two are added. This is a summation node. So they both have the same input, but their outputs are added, and that's the output of the whole system. And also for this system, we can calculate the transfer function of the whole thing by looking step by step how this works. So H1, for example, it has input X. So then we know that the output of H1 has to be H1 times X. That's how it works. In the Laplace domain with the transfer functions, just multiply transfer function with the input, you have the output. Same for H2. It also has the input X. Same input is going to H2. So its output is H2 times X. And these two are added. So then we have, as the output of the whole system, we have H1 times X plus H2 times X. Or in other words, the transfer function of this whole system, that's output divided by input, that's H1 plus H2. So this is the summation rule that applies when we have two parallel processes with their outputs added here in the end. Both of these rules, even if you forget them, you can easily deduce them by yourself again using these intermediate steps that I also show here in the slide. The last one, that's the loop reduction rule. That is this here. So then we again have two separate systems, H1 and H2, but now they are combined using a loop reduction rule. So you're using a feedback loop. And to calculate the output, we have the loop reduction rule. So we have an input X, which is going into this subtractor, plus and minus. The output of that subtractor, so the difference between X and this feedback value, that's the input for H1. And the output of H1, that's the output of the whole system. But that output is also going here into H2. And the output of H2, that is the feedback value over here. So the output Y, of course, it will depend on X and some kind of combination of H1 and H2. How can we get a hold of that transfer function? Well, again, by looking at it step by step. So if you look, for example, at H2 first, the input of H2 is Y, because it's connected to the Y output. So the output of H2 must be H2 times Y. That's how it works. For any system, the output is the input multiplied by the transfer function. So the input for H2 is Y. So the output for H2 is H2 times Y. So that is the value that's going into this subtractor and also X. So what this subtractor does is it subtracts X and H2Y. It was already there visible in the slides. The output of this subtractor is X minus H2Y. Very simple, very straightforward analysis of this system. So far, we're not finished yet, but this is the next step. So the first step to analyze this system and find the transfer function is recognizing that H2, the input of H2 is Y, so the output is H2 times Y. For this subtractor, the input is X and H2 times Y, so the output is X minus H2 times Y. And then we can calculate Y because we now know the input of H1, that's X minus H2 times Y. So then we can calculate the output, that it must be H1 times X minus H2Y. It must be this. The output of H1 is H1 times its input, and its input is X minus H2 times Y. And that is the same as Y. So Y, that is Y. So the Y is H1 times X minus H2 times Y. So here we find an equation which contains one unknown, Y, and we know the input. We know H1 and H2. So now we have one equation where there's one unknown value, that's Y. So with a bit of mathematical rewriting, we can deduce Y from this. Well, what the first rewriting step we do is to get rid of the brackets. So H1 times X minus H2Y is the same as H1 times X minus H1 times H2Y. And that's distribution law in algebra. So then we know that we can take this factor here, H1 times H2 times Y, and bring it to the left. So then we get Y plus H1 times H2 times Y is equal to H1 times X. That's what we have left on the right. That's being left on the right. So then we find Y plus H1 times H2 times Y is H1 times X. Now we have Y on one side, X on the other side. Then again, distribution. So we have a Y here at both places. We can take it out of the brackets. It's Y times 1 plus H1 H2 is equal to H1X. And finally, we can calculate the transfer functions, Y divided by X. And we could also have calculated Y, but actually we are interested in transfer function, so that's Y over X. And Y over X is H1 divided by 1 plus H1 times H2. So that is the loop reduction rule. And the transfer function of this whole system, including the feedback loop, that is defined as Y over X, output divided by input in the S domain. And following the steps in the calculation, we find that is H1 divided by 1 plus H1 times H2. And that's what we call the loop reduction rule. So you are supposed to try to memorize that, H1 divided by 1 plus H1 times H2. If you cannot memorize it, if you forget it, you can still follow the same steps that I did here to deduce it by yourself again. But of course, it's easier if you try to memorize this. So all these three rules, I'll go back to the first one. The product rule, if you have two processes in a row, you simply multiply the transfer functions. That's the product rule, easy to remember. Summation rule, if you have two processes in parallel and the output added, then the transfer function is the sum, H1 plus H2. And if you have a loop, and of course, that's what we will use. That's the most important one for us. Maybe it's not the one we will use the most of the times, but it's the most important one for us. If you have a reduction, a loop, a feedback loop, then the resulting transfer function is H1 divided by 1 plus H1 times H2. That are the three reduction rules. An example of a feedback system. Suppose again you have an amplifier. But in this case, we don't know exactly how much it amplifies. So that's an op-amp. It's just amplifying with a very high factor. For our calculations, we can actually assume it's infinite, but in reality, it will be a high factor like 10,000 or 100,000 at 10 to the power 4 or 10 to the power 5. That's what this op-amp does. It takes its input and multiplies that with a very high factor, amplifies it with a very high factor. An op-amp has actually two inputs, and these will be subtracted. That's why there is a plus and a minus here. So the input on the plus and the input on the minus, they will be subtracted. And that result will be multiplied by that high factor. We have the plus here connected to X. We have the minus connected to this voltage divider, which is connected to the output of the op-amp. And this is the feedback value. So the question is to analyze this system using the reduction rules that we just saw, rewrite it in a simpler form, and then give the resulting transfer function. Again, I would suggest to first try it yourself. So stop the video, pause the video, and then compare your solution to mine. So here we have the same diagram again. This is, let's say, the electronic diagram of this system. There's the op-amp over here and the voltage divider over here, and our output is Y. This is not the type of diagram that we use for our processes and for our feedback loops. So let's redraw that in such a form that it resembles the process diagrams that we have been using so far. Or in other words, let me state it otherwise, this diagram that we have here on the left, that's not something you can enter in MATLAB in Simulink, because we don't have an op-amp in Simulink, and we don't have this voltage divider and resistors and ground value and so on. So we have to redraw that diagram in such a way that it could be entered in MATLAB. Then it's a process diagram. So if we look at the op-amp first, the op-amp is actually a combination of two components. It's a subtractor, it's plus minus, followed by a block that simply multiplies by A0. So this one has transfer function A0, and A0 is just some high value. And in front of that, so actually in this triangle, you have a combination of this subtractor and a simple transfer function that only multiplies with a fixed value. This is connected to the input X, so that could be a step input, for example. And this output here, it's connected, this is Y, to a second process, and the output of that process is going to the minus over here. And this block models this voltage divider. We have done that in the first week, I think, or the second, I'm not sure. There we calculated the transfer function of such a voltage divider. I hope you remember that. If not, then look it back. But this voltage divider is actually a process that has a certain input Y and multiplies that input by R1 divided by R1 plus R2. That's also a simple constant. Right? It's a formula, but if you calculate that formula, you get a constant value depending on R1 and R2. And also here for this A0, it's a constant value. That's a big value, somewhere between 10,000 and 100,000, but it's constant. So actually both of these are zero-order systems. Zero-order systems are systems that just multiply the input with a fixed value, and then you get the output. So this is zero order, and this one is also zero order. But what we have to do is we add arrows to show the direction of things. What we have to do is calculate the transfer function of this whole system. That's our goal. We want to calculate the transfer function of this whole system. Well, that's easy. We know the loop reduction rule. We just saw that. We have already determined our h1. H1 is this, and h2 is this. So then simply by using the loop reduction rule, we can calculate the transfer function of this whole system. So the ht, the h total, let's call that h total. That is loop reduction rule. Remember, that's h1 divided by 1 plus h1 times h2. We just saw that rule. And that is, well, h1 is a0. And here we have 1 plus, again, h1, so again, h0, multiplied by h2, and h2 is r1 divided by r1 plus r2. So this is our transfer function for the whole system. Notice that this is, again, a constant. We only have a0, which is a constant, r1 and r2 in it. They are all constants. So this will be a constant value again. So also the whole system will be zero order again. It will just multiply its input with a certain value. There's one thing we can do. We can make use of the fact that we already know that a0 is a big number. So a0 is big. That's what we have in an op-amp. It multiplies with a big value. It amplifies with a big value, 10,000, 100,000, or maybe even more. I don't know exactly. But if a0 is big, then especially this is interesting. If we somewhere find the factor 1 over a0, then that will be almost zero. It can be disregarded. It can be ignored. Well, looking at this formula that we found for the transfer function, we don't have a 1 over a0, but I can rewrite it such that we get it, because I can divide both sides by a0. So if I divide this by a0 divided by a0, we get 1. It's a0 divided by a0, then we get 1. And if we divide this here by a0, then we get 1 over a0 plus r1 divided by r1 plus r2. And we are getting rid of this factor a0 because we divide by a0. And now we have this 1 over a0 over here. And we know that a0 is big. So this factor here, that's almost zero. That's nothing, almost zero. So we can ignore it, which means shift it a bit, which means that the whole thing reduces to this. So we have 1 divided by a0, but it's 0, plus that. So that's 1 divided by r1 divided by r1 plus r2. And rewriting that, that's the same as r1 plus r2 divided by r1. So that is our final transfer function. This whole system there, which is a redrawing of that diagram, that electronic diagram that we have there, that has as a transfer function r1 plus r2 divided by r1. Here we are making use of the loop reduction rule. That was this here. And we are making use of the fact that A0 is big, which means that 1 divided by A0 can be ignored. That's almost zero. Big means in this case 10,000 or 100,000, somewhere in that order of magnitude. And that's what you often do with an op-amp. You don't know exactly how much it amplifies, but you know it's a big value. So then you can ignore certain parts in your formula, and then your end result is simplified to, in this case, this R1 plus R2 divided by R1. So this is the total transfer function of this system with the op-amp and the voltage divider.